In this part of the problem, we're going to look for two different values, the expectation value of momentum, as well as the expectation value of the position squared. As you can see, the expectation value of momentum isn't going to take too much effort. We can think of it in terms of the classical sense of the mass times the velocity, or the time derivative of position. And since we're talking about expectation values or the average values, we're just going to take the average value of position. Now, in the first part of the problem, we found this was actually equal to 0. So the time derivative of 0, of course, is just going to be equal to 0. And that's what we would expect the average momentum of a simple harmonic oscillator bouncing back and forth with a direction in both this way and a direction in both this way, on average, will be right in the center, will be equal to 0 here. Now, moving on to the expectation value of the position squared, it's not too bad. It's actually kind of fun to do, but it's not as simple. So, of course, with any expectation value, if we're going to have to do it by integration, we're going to have to sandwich the respective operator in between the complex conjugate of the wave function and the wave function. So I'll go ahead and put it in brackets here because there's going to be parentheses in the middle. So in the textbook, it describes the operator for the position squared to be as follows. So that is the expectation value. That is the representative operator for the expectation value squared. If you're a little confused on what this came from, I recommend you go into the textbook and you review that section. But regardless, that is going to be sandwiched in between the two wave functions here, and then dx here. Now, the next step is we can go ahead and pull this glob of constants out in front. And then I'm just going to put the integral sign just to save some time. Now, the next step is we're just going to go ahead and distribute this wave function to the constituent linear components. I'll go ahead and put in a bracket here too. It's always nice to organize everything in brackets and parentheses. And sometimes when things get really fun, you can use curly brackets. Oops. That's okay. We'll just go ahead and throw the wave function in here. In brackets, overall space. Now, as you can see, we need to evaluate these linear combinations right here. These are the raising and lowering operators. And so I'll go ahead and just explicitly write, let's just go ahead and move this whole thing down to make room for some notes here. There we go. Now, if we look at just this one right here, that's the same as the raising operator acting on the raising operator acting on the wave function in some arbitrary state psi sub n. Now, when the raising operator acts on psi sub n, it raises it to the n+1 state, the next state, and then it also raises it and multiplies it by the state that it was raised to. Now, when we do that again, that raising operator right here can move through that constant and operate on that wave function. And so if we go ahead and move that n+1 out of the way, it'll raise it to the next highest state, which is n+2, and then multiplies it by the square root of that state that it was raised to, n+2 here. So that is what this is equal to here. Now, this is less important right now for this problem than this sign right here. The fact that when you have the raising operator acting on it twice, it'll raise it to the n+2 state. Now, if we look at this one right here, we know it's going to do something similar and have some sort of constant out in front, but it's going to lower it 2 times to the n-2 state. All right, let's just keep that in the back of our mind. Now, if we look at these, that's the same as the raising operator acting on the lowering operator on some psi sub n state. So we know it's going to lower it to some psi sub n1 state, And when the lowering operator acts on something, it just multiplies it by the state it was once at. So that it was previously at the end state. So it's going to be times the square root of n. Now, whenever we throw this raising operator on this one, it'll move it back up to the n state. But then whenever the raising operator goes and acts on the state, just like how we set up here, it multiplies it by the state that it's currently at. So that state is now currently in the state n. So that's what that is equal to. Now we go ahead and apply that to this one right here. Same thing, the lowering operator acting on the raising operator. Let's just go ahead and put it on there. So it raises it to the psi sub n plus 1 state and then multiplies it by that state that it's currently at. Now when we do that, throw the raising operator again, or the lowering operator again, it'll lower it back down to that psi sub n state and then multiply it by the square root of the state that it's currently at. Oops. Or currently it was at. Previously it was at. So it's n plus 1. And all right, so that's the important part right here. These will be important later, right? But the more important part right now is that these are back at the end state. So now let's look back at this whole glob that we have right here. We'll go ahead and pull this glob of constants down. They're important, but we just need to concentrate on something else. I think I need to give myself a little bit more room. Let's just go ahead and bump it down right there. I think that's nice. Now we go ahead and put that integral. This complex conjugate's just waiting to do something fun. Now we'll go ahead and substitute in everything that we did solve for here. For these ones, these two, I'm just going to put parentheses, ... to represent some sort of constant, which are important, but not necessarily for this problem right now. But we know that's the psi sub n plus 2 state, plus what we had here, which is just going to be n times psi sub n. And then what we had in this part right here, which is going to be parentheses n plus 1 for the psi sub n state, and then some glob of constants n minus 2 state, and bracket overall space. Now we'll go ahead and distribute this integral and complex conjugate onto each one of these constituent linear combinations. And again, let's go ahead and shift this glob of constants down. All right, we're going to need a bracket here. So now we have a bracket. We're going to have a bunch of integrals. And while we make these integrals, let's go ahead and pull these constants out in front of the integral too. So for the first one, we'll have those constants times a psi sub n state complex conjugate times a different state, overall space, and so forth. Let's just go ahead and do that now. Okay, I'm just going to go ahead and shift this up. So let's see here. Let's go on to this next page here. Go all the way down. There's our constants. So as you can see, this is going to be the probability density found for this space, but that's the overlap between these two orthonormal states. So think about it as the dot product between two things that are completely and utterly that have no overlap, right? So that overlap is going to be 0. And you can think of this one as the dot product of things that have complete perfect overlap. So that's just going to be 1. So we're going to go ahead and I'll just do it explicitly here. So this is going to be 0. And this is an important concept I think that we learned earlier in chapter 2, but for the most part, we'll be coming back to this. This is one of the main important ideas in quantum mechanics. Let's go ahead and put a bracket here. So all that's going to be left. So this is going to be 0 plus, this is 1, but we still have the constant out in front, which is n. Same thing with the next one, which was just n plus 1 plus 0. All right, and we'll go ahead and expand these constants that we had. We're no longer going to drag and drop them. I have to remind myself what they were. So it was h bar over 2m omega. Now this is going to be multiplied by 2n plus 1. And that's our final answer for the position squared expectation value. If we scroll all the way up here, let's get it all in there. Yep, so pretty fun problem. It's good to know about these little relations here. And it really highlights the utility of these raising and lowering operators, because these would have been nasty integrals if we didn't have those.